Hi everyone, my name is Kado from La Trobe University, Australia. I'm pleased to present our paper titled RobSense, a robust multimodal foundation model for remote sensing with static, temporal, and incomplete data adaptability. This is the outline of my presentation. Remote sensing data refers to information gathered about objects or areas from a distance, without making physical contact. This data is typically collected through satellite missions, drones. It plays a crucial role in Earth observation applications such as land use and land cover analysis, urban planning, environmental monitoring, and more. There are two commonly used types of sensors. First, optical sensors. These detect and measure electromagnetic radiation, essentially capturing the light reflected from the Earth's surface. They produce what's called multispectral, or MS images, which include data from multiple wavelengths across the visible and infrared spectrum. Second, radar sensors. These are particularly powerful because they can collect data in all weather conditions and at any time of day or night. Radar sensors generate synthetic aperture radar, or SAR data, which is especially useful when visibility is limited due to clouds, darkness, or fog. Both types of data provide rich, high-dimensional inputs that are ideal for training machine learning models to detect patterns, classify land cover, or monitor changes over time. However, traditional deep learning models typically require a large amount of labeled data, which can be time-consuming and costly to obtain, especially in the context of satellite imagery. At the same time, there is a massive amount of unlabeled remote sensing data, especially from satellite missions like Sentinel, that often goes underused. To bridge this gap, designing multimodal foundation models using self-supervised pre-training has become increasingly important. This approach allows us to leverage both multispectral and SAR data without relying heavily on labeled datasets, making it far more scalable and efficient for real-world applications. While foundation models offer a promising path forward, existing remote sensing foundation models still face two major limitations. First, they often support only limited input types, making it difficult to fully leverage the diversity of remote sensing data, such as both multispectral and SAR. Second, they don't handle incomplete data well. Things like missing spectral bands or irregular time series are common in real-world satellite datasets, but current models struggle with them. To address these gaps, we propose RobSense, a robust multimodal foundation model for remote sensing. RobSense is built with a modular design and is pre-trained using temporal multimodal learning and masked autoencoders. This allows it to learn from diverse inputs more effectively. And to specifically tackle data incompleteness, we introduce Now, let's take a closer look at our proposed method, illustrated in this diagram. Our pre-training framework consists of two key phases. First, temporal multimodal learning. In this phase, we leverage time series data from multiple modalities, such as multispectral and SAR. We introduce temporal distribution alignment (TDA) to ensure that the model captures and preserves time-specific patterns and distributions across modalities, which is crucial for understanding dynamic Earth processes. Second, latent reconstruction learning. This phase focuses on handling incomplete or sparse remote sensing data. Here, the model learns to recover rich latent representations, even when some spectral bands or temporal observations are missing, making the model robust in real-world scenarios where perfect data is rare. Together, these two phases make RobSense both temporally aware. Let's now dive into phase 1 of our proposed method, which focuses on temporal multimodal learning. We introduce temporal distribution alignment, or TDA, which ensures that representations from multispectral and SAR modalities at each time step are aligned. This is achieved by modeling both sets of representations under a shared Gaussian distribution and minimizing the Kullback-Leibler divergence between them. Mathematically, the KL divergence measures how much one distribution diverges from another. In our case, how different the temporal representations of multispectral and SAR are. Our total TDA loss combines KL divergences in both directions to enforce symmetric alignment. In addition, we apply an autoencoder loss, which drives the model to learn robust representations by reconstructing masked input patches. This forces them. Moving on to phase 2 of our method, latent reconstruction learning. This phase is designed to handle missing or incomplete data, which is very common in remote sensing due to two main issues. First is about variability in the number of spectral bands, for instance when different satellites capture different band configurations. Second is about irregularities in the temporal sequence, such as gaps or inconsistencies in data collection over time. To address this, we simulate missing data and train the model to reconstruct rich latent representations from these degraded or incomplete inputs. As shown in the equation, we use a mean squared error, MSE, loss, to minimize the distance between the reconstructed latent representations and the original, full representations, for both multispectral and SAR modalities. This reconstruction learning ensures that our model remains robust and informative. Let's now take a look at our experimental setup and evaluation. For pre-training, we use the SATLAS dataset, a large-scale, multimodal remote sensing dataset, and adopt a YT-based encoder to learn generalizable representations. For evaluation, we test our model on 3 diverse downstream tasks: segmentation, evaluated again on SATLAS, classification using the Big EarthNet benchmark, and change detection, assessed on the OSCD dataset. To benchmark performance, we compare RobSense against several strong baselines, including StatLessNet, SpectralGPT, Sama A++, and Chroma. Right, now let's take a look at the quantitative results. As shown in the tables, our model consistently outperforms the baselines, and what's especially notable is this. The performance gap widens as the amount of missing data increases. This clearly demonstrates the strength of our latent reconstruction module, which is specifically designed to recover rich representations even when input data is sparse or degraded. In other words, RobSense becomes even more effective under challenging conditions, highlighting its robustness and real-world applicability. These are about qualitative results. They illustrate that RobSense effectively captures seasonal changes in dynamic areas, such as shrublands and crop fields. We examine the impact of two key factors, temporal distribution alignment and latent reconstructors. Due to computational constraints and these factors being less influenced by data scale, the model is pre-trained on 5% of the dataset, with Big EarthNet used for fine-tuning on static multimodal input. As you can see, TDA significantly enhances latent representations by aligning the distributions of both modalities consistently over time. Training latent reconstructors separately can effectively handle missing data by preserving rich representations. To conclusion, diverse model foundation model for remote sensing. RobSense is designed to seamlessly integrate both multispectral and SAR data while directly addressing two major challenges, supporting diverse input types and handling incomplete data, which is common in real-world scenarios. Our approach uses parallel unimodal encoders alongside a shared multimodal encoder and incorporates two pre-training strategies, temporal distribution alignment to preserve time-specific patterns and masked autoencoding for learning complete representations from partial inputs. Two unimodal latent reconstructors help rebuild rich features even when data is missing, be it spectral bands or time systems. RobSense shows strong and consistent performance across both complete and incomplete datasets. Thank you for your attention.